Friends, welcome to the lecture of real analysis. We are studying series of infinite series of real numbers, and in the last lecture we have defined the convergence and divergence of infinite series. Now today in this lecture we shall study series with non-negative terms, and then we shall study special type of series, which is geometric series and harmonic series. So first we shall consider this result. But what is the meaning of series of non-negative terms? It is clear that each term of the series is non-negative. So we may consider this series summation of n square. Then what will be, as n takes values from 1 to infinity, then the terms of this series will be 1 square, 2 square, 3 square and so on. So this can be considered as an example of series of non-negative terms, or the series n plus 1 divided by n taking value 1 to infinity. So what is the first term? Put n is 1, so it is 2 by 1, next term is 3 by 2, and next is 4 by 3, etc. These are examples of a series of non-negative terms. So which is not in series of non-negative terms? If you consider summation n takes value 1 to infinity minus 1 to the power n, then what will be the first term of this series? Or we may consider n plus 1. What is the first term of this series? Minus 1 to the power 2, and that is plus 1. And what is the second term of this series? Minus 1 to the power 2 plus 1, that is minus 1 to the power 3, which is negative 1. And similarly the next will be positive, because we know that minus 1 to power n or n plus 1 depends on whether n plus 1 is even or odd. If it is even, then the value is positive 1, and if it is odd, then the value is negative 1. So therefore the terms here are alternate positive and negative, and so on. And this is not an example of series with non-negative terms. Such series we should not consider. Only the series of this kind we shall consider, whose each term is non-negative. Maybe 0, but it must not be negative. So that type of series we are studying in this article or in this section. Now the result we have written as theorem number 3 in serial order, and the result is, or the theorem is, if sigma an is a series of non-negative numbers with Sn, and we know Sn is sum of first n terms, a1 plus a2 up to n belongs to I, integer, positive integer, then first part is a sigma an converges if the sequence Sn, this sequence Sn is bounded, and second is sigma an diverges if Sn is not bounded. So that means the convergence of non-negative series of non-negative terms is expressed in terms of bounded and unboundedness of the sequence of partial sum. That means if the sequence of partial sum is bounded, then the series is convergent, and if it is not bounded, Sn is not bounded, then the series is divergent. Earlier by the definition we have for convergence of series is, if Sn is convergent, then sigma an is convergent. That we have defined. Convergence of series is defined in terms of convergence of the sequence of partial sum. It is same. If Sn is convergent, the series is convergent, and if Sn is divergent, the series is divergent. So instead of convergence, it is written in terms of bounded and not bounded. So that we shall now do. So we now consider proof for part A first. Because the series is of non-negative term. Each term of the series is non-negative, and therefore we have, or we can write, since an plus 1 is non-negative, means greater than or equal to 0. So we have Sn, or we shall consider Sn plus 1 is equal to. Now how Sn plus 1 can be written? This is Sn is given. So Sn plus 1 means sum of first n plus 1 terms, and that is a1 plus a2 up to last will be an plus 1. and earlier will be an. So this is, and but now what is this? This is equal to Sn. This much a1 plus a2 up to an is Sn, and the last is separate term an plus 1. And we know this is greater, Sn an plus 1 is greater than or equal to 0. So therefore this becomes greater than or equal to Sn. It is a non-negative quantity, and therefore Sn plus non-negative quantity becomes greater than or equal to Sn. N belongs to I. And that is Sn plus 1 is greater than or equal to Sn for n belongs to I. So what this suggests that this sequence Sn is non-decreasing. The terms are increasing. So therefore the sequence Sn as n tends value from 1 to infinity is non-decreasing. Non-decreasing, and see, in the hypothesis of the theorem it is given bounded, and by hypothesis, or it is given in the theorem by hypothesis. We are considering first part proof, so we have to assume it is bounded, then this is convergent, and by hypothesis bounded. So thus what type of sequence Sn becomes? It is non-decreasing and bounded means it is bounded above, or you may write it is bounded because it is increasing. So when it will be bounded? If it is bounded above, and thus a non-decreasing sequence which is bounded above is the Sn, and we know that if Sn is a sequence which is non-decreasing and bounded above, then it is convergent. Thus this is theorem we have proved in the chapter of sequences. Thus Sn is convergent, and if a Sn is convergent, then the series becomes convergent. That depends on the convergence of Sn. So bounded implies convergent here because it is non-decreasing and bounded above. Thus Sn is convergent, and hence the series sigma an as n takes value 1 to infinity is convergent. So here condition becomes simpler for non-negative series, series of non-negative terms. Instead of convergent, it is sufficient to show it is bounded, and then the series becomes convergent. Now B part. Now in the second case, what happens if Sn is not bounded? If Sn is not bounded, then it is already non-decreasing. We have shown here it is not decreasing and not bounded. If Sn is not bounded above or not bounded, then Sn is a non-decreasing sequence. And not bounded above. So therefore Sn is divergent. So this also result we have proved in the chapter of sequences. A non-decreasing sequence actually increasing and which is not bounded above will diverge to infinity. So therefore Sn diverges, or that is Sn diverges to infinity as n tends to infinity. And if Sn diverges, the corresponding series sigma an diverges. Therefore summation of an as n takes value 1 to infinity diverges, and this proves the theorem. So here for a series of non-negative terms, the convergence of the series, convergence or divergence depends on the boundedness of the sequence of partial sum. If it is bounded, the sequence series converges. It is not bounded, the series diverges. Now we shall consider next type of series, and that is a geometric series. So first we write as a note what type of series is known as a geometric series and how it is denoted. The series summation x to the power n, and n takes value 0 to infinity. So if n takes value 0 to infinity, what is the first term? X power 0 is 1, and x power 1, that is x, next will be x square, and so on. And generally is x to the power n, but it is infinite, continued further. So is known as geometric series. So this type of series, and generally we denote the series summation from 1 to infinity, but for geometric series we denote the sum from 0 to infinity, because the first term is 1. So you should note this change. For geometric series we write summation from 0, 1 to etc. And now the second, we may suppose this as first result. The second result we want to use it further is this one. So we have the sum 1 plus x square, sum of first n terms, n minus 1. See, last term we have written x to the power n minus 1. So here from onwards it will be n minus 1, and the first without x is one more term. So total terms are n. And this is a geometric progression whose first term is 1 and common ratio is x. So consecutive terms, if you divide the next term by the earlier term, we get every time x, and x is common ratio. So therefore the sum is given by this formula. It is 1 minus x to the power n divided by 1 minus x, if x is less than 1, and or if x is greater than 1, we write as x to the power n minus 1 divided by x minus 1. If x is greater than 1. And what is x is equal to 1? What will be this sum? It is obvious. If x is 1, each term becomes 1. And how many terms are these? N terms. So therefore, this will be exactly n if x is equal to 1. So actually we want to use this first result. Sum of first n terms of this geometric progression is 1 minus x to the power n divided by 1 minus x. Now we shall state theorem related to this geometric series, and that will be our theorem number 4. So when the geometric series is convergent and when it becomes divergent, that we shall see. So it is theorem now 4. It has two parts. First, if 0 is less than x is less than 1, then the series x to the power n takes value 0 to infinity, converges and exactly to 1 divided by 1 minus x. That is first result. And B, second result is if x is greater than or equal to 1, then the series summation, again the same series, geometric series, x to the power n diverges. So these are the two results in the theorem 4. Now we shall consider the first result, proof for first. We shall form a Sn, that is sum of first n terms. So here we have Sn. Sn is equal to, what is the first term of the series? Actually the series is written here. and therefore the sum of first n terms starting with 1 plus x square and so on. But what is the last? The last will be not x to the power n but x to the power n minus 1 as written here, because this one is separate and these are in terms of x. So x to the power 1. Then if you consider this from second onwards, then these will form n minus 1 terms, and this is earlier first term, so total terms will be n, and therefore last we should write x to the power n minus 1, and thus we should add this using the relation or formula, and we have written for that purpose this formula is written 1 minus x to the power n divided by 1 minus x, or this is the condition here. We have 0 is less than x is less than 1, and therefore Sn is this one, and that becomes 1 minus x to the power n divided by 1 minus x. Now we shall take its limit. Therefore limit of Sn as n tends to infinity is equal to limit n tends to infinity of 1 minus x to the power n divided by 1 minus x. And you see, if we take this limit, then 1 and x are constant with respect to this limit. So therefore this will be actually limit, it is 1 minus limit we have to take for this term as n tends to infinity of x to the power n divided by 1 minus x. And what is this limit? If x is less than 1, then this will tend to 0. This we have studied in sequences. It is a geometric sequence with the common ratio less than 1, and it converges to 0. So therefore this is 1 minus 0 divided by 1 minus x, since limit n tends to infinity of x power n is 0, as 0 is less than x is less than 1. So therefore that's what we have, limit of Sn. Limit of Sn is 1 minus x. So we have used this, and therefore limit n tends to infinity of Sn is equal to 1 upon 1 minus x, and thus hence the series summation n takes value 0 to infinity x to the power n converges to the same limit 1 upon 1 minus x. In the case 0 is less than x is less than 1. So thus this proves part A. Now we shall consider part B. What is given in the second part? X is greater than or equal to 1. If x is greater than or equal to 1, then we will have x to the power n will also be greater than or equal to 1, or 1 to the power n, and but 1 to the power n we know it is 1. So thus therefore if you take the limit n tends to infinity of x to the power n, this will be certainly greater than or equal to 1. Limit on both sides, and that is 1, greater than or equal to 1. Or therefore that means limit n tends to infinity of x to the power n is not equal to 0. It is greater than 1 means certainly it is not equal to 0. And now we use the theorem second, contrapositive statement. If limit of nth term of the sequence is non-zero, the series or limit of nth term of the series is not equal to 0, then the series is divergent. So this shows that, or this proves that summation x to the power n as n takes value 0 to infinity. Here the condition is x is greater than or equal to 1 is divergent. If x is greater than or equal to 1. This we have written by theorem number 2. You should refer that theorem. Theorem 2. What is the theorem 2? If sigma an is convergent, then limit of an is 0. And if limit of nth term is not 0, then the series is not convergent, or that means it is divergent. So thus this series divergent if x is greater than or equal to 1, and is this series converges to if x is between 0 and 1. So thus the two cases we have considered separately, and this proves the theorem. Theorem number 4 we have. Now one more result we can consider for harmonic series, and we may write a note for harmonic series. So the series summation 1 by n. Here n will take values 1 to infinity. Only for geometric series we are considering n taking value 0 to infinity. So you note this, and that is the first term is obvious 1. 1 over 1 is 1 plus 1 over 2 and 1 over 3 and so on. The general term is 1 over n plus so on. E is known as harmonic series. Now we state a theorem about this. What about the convergence of harmonic series? And this harmonic series is divergent. That we shall state as our next theorem. Theorem 5. The series summation 1 over n, n taking value 1 to infinity, is divergent. Obviously divergent to positive infinity, because we are studying only the series of non-negative terms in this section, and therefore this is divergent and diverges to infinity. So we shall prove this. What is Sn? We have here sum of first n terms. We have Sn is equal to, Sn is 1 plus, you may observe this, sum of first n terms, and it is exactly the same here up to 1 by n. 1 plus 1 by 2 plus 1 by 3 and so on up to 1 by n. This is Sn. Now we have to decide the convergence or divergence of this sequence Sn. If it is convergent, then the series will converge, and if it is divergent, the series is divergent. Actually here we have to show that this Sn is divergent, then the series becomes, corresponding series becomes divergent. And to show Sn is divergent, we shall show a subsequence of Sn is divergent. And we know the result as if a subsequence of a sequence is divergent, then the sequence is also divergent. And for this purpose we examine the subsequence. Now the subsequence we shall consider as S1, S2, S4, S8, and general term will be in powers of 2. See here, 0th power of 2, first power, second power, third power, and in general nth power of 2. We shall examine the subsequence, this subsequence. Now we have, what is S1? You see, S1 is A1, and A1 means 1. So S1 is equal to 1. What is S2? S2 is 1 plus half, and 1 plus half is 3 by 2. And what about S4? We have to consider these terms only. This is a subsequence of this sequence Sn, S1, S2, S3, etc. And we are considering selected only those terms, S2 power n. S4 we should write in terms of S2. So I shall write S4 as S2 means sum of first two terms, and what are remaining? Third and fourth, A3 plus A4. You note this. S4 is A1 plus A2 plus A3 plus A4. But what is A1 plus A2? A1 plus A2 is S2, and therefore this is S2 plus A3 plus A4. And what is now S2? S2 is 3 by 2. Here it is exact. So S2 is 3 by 2, and plus what is A3? Third term of this see, of the series, third term of the series is 1/3. 1/3 plus the fourth term is 1/4. And now we shall compare the terms only. Instead of getting the exact value, we shall compare the terms. And I shall write this as 3/2 and plus 1/4 plus 1/4. And what is the relation between these two terms? See here, I have replaced 1/3 by 1/4. So 1/4 is less than 1/3 because here the denominator is smaller, the value is greater. And therefore this expression is greater than this one. And we have purposefully written for comparison. We have replaced these terms by last term, 1/4. 1/3 is replaced by 1/4, and thus this value becomes greater than this one. And what is this number that we shall write? 3/2 plus 1/2, or that is actually say 4/2, or which we can write as 2. So this is 2. Now asset. Next is asset. Asset we shall write in terms of S4. Here S4 we have written in terms of S2. So I shall write S4, and remaining 4 terms will be there from SA5. So first 4 terms are added here. Now remaining terms we should write separately: A5 plus A6 plus A7 plus A8. And this is equal to, or instead of equal to, we should use this relation because S4 is greater than 2. So I shall write this is greater than 2 plus. And what is A5? A5 from this generally is 1/n, and therefore A5 will be 1/5. 1/5 plus 1/6 plus 1/7 plus 1/8 up to A8. And now you see this is we replace these three terms by the last term, that is 1/8. And I shall write 2 plus 1/8 plus 1/8 plus 1/8, and last also as 1/8. So you see this is, now this above expression is greater than this, as the same reason here the denominator is smaller than this denominator, and therefore the value is greater. Corresponding terms are greater, and therefore this is greater. This is greater than this. And but what is this sum? This is 4/8, means 1/2 again, and 2 plus half. 2 plus half is 5/8. So therefore this is equal to 5/8. That we will write. The asset is greater than 5/8. And now we observe these terms again. See, what we have written is S1. S1 is equal to 1, S2 is 3/2, and S4 is greater than 2. But that can be written as S4 means S2 square is greater than this 2 plus 2 divided by 2, which is again 2. And this asset can be written as S2 power 3. 8 is 2 power 3, and that is greater than, which is 5/2, but 5/2 we can write as 3 plus 2 divided by 2. So here thus we have S, and likewise what will be the next term? 2 power 4, 16, S16 will be greater than 4 plus 2 divided by 2. And this first also satisfies the relation S2 power 1. S2 means S2 power 1, and that is actually here greater than, it is equal to, here it is equal to, see, 1 plus 2 divided by 2, that is 3/2. And the first also S1 power 1 is 1 plus 1 divided by 2, and that is 1. So each term is of this form. And you observe from this fourth term, S4, S2 square is greater than 2 plus 2 divided by 2 means 2. Asset, that is S2 cube, is greater than 3 plus 2 divided by 2, that is 5/2, which is the same. And in general, or not in general, but for next term. And what will be in general? In general, if I write S to the power n, that will be greater than which? By observation of these. See, here is third power, we have written 3 plus 2 divided by 2. Fourth power may be written as 4 plus 2 divided by 2. Second power 2 plus 2 divided by 2. All we have verified up to this. here these first two are equal but next becomes greater, and therefore s 2 power n will be greater than n plus 2 divided by 2. So this is the general relation for the terms, comparison of the terms, and we will now write this and so on. So and so on. In general, it can be shown by induction, method of induction, that the result is true for n is equal to 1. If it is true for n is equal to m, then it is true for next value of n, etc. So it can be shown by induction that s to the power 2n, s of 2 to the power n is greater than n plus 2 divided by 2, or n greater than 2. N greater than 2 means from 4, 8 onwards. And now we will take the limit of this. So therefore, limit n tends to infinity of s 2 power n will be certainly greater than or equal to limit of this is greater than or equal to limit n takes values, n tends to infinity, n plus 2 divided by 2. And what this shows, this limit is infinity, and therefore this is greater than or equal to infinity means this must be infinity. So this is actually infinity, and thus limit n tends to infinity of s 2 to the power n is equal to infinity, and therefore the subsequence, this is subsequence of the original sequence, diverges to infinity, or therefore the subsequence s 2 power n of Sn, this is a subsequence of original sequence Sn, diverges, and therefore if the subsequence of a sequence diverges to infinity, the sequence also diverges to infinity. This result we have studied in the chapter of sequences, and therefore Sn diverges to infinity. And if Sn diverges to infinity, what is Sn? Sn is sequence of partial sum of this series. So this series must also diverge. So therefore the series is divergent. And this completes the proof of the theorem. So thus we have proved the theorem. We have studied here in this lecture series of non-negative terms, and when the series is convergent, if the sequence of partial sum is bounded, it is convergent. And secondly, we have considered geometric series. When the geometric series is convergent, if x to the power n is convergent, if x lies between 0 and 1, and the harmonic series is divergent. So these things we have studied in this lecture. So remaining part we will continue in the next lecture. Thank you.